Welcome to this explainer. For thousands of years, humans have looked up at the stars and just wondered what it would actually take to reach them. Well, it turns out it's not just about building a massive engine. It's really about conquering the invisible chains of physics that hold everything to the ground. Let's get into it. So let's kick things off with a massive thought experiment to establish the stakes. What exactly prevents a rocket from just launching into the sky, pointing its nose upward, and floating away forever? I mean, it sounds simple enough, right? But the reality is gravity isn't just some force acting down here on the surface. It's an invisible tether that extends way out into space. As a rocket climbs, gravity is relentlessly pulling it right back down toward the center of the Earth. To actually leave, you can't just fly up. You have to fundamentally outrun the pull of the entire planet.
Here is the roadmap for today's explainer. We're going to start with the gravity problem, move on to reaching cosmic velocities, explore liquid and nuclear power, and wrap up with the multi-stage solution.
All right, section 1, the gravity problem. To really wrap your head around this, picture a giant cannon placed right on top of a massive, incredibly high mountain. We're talking sitting right above the Earth's atmosphere. Now, if you fire a projectile horizontally from this peak and there was absolutely no gravity, it would just fly perfectly straight out into the void. But because of gravity, that projectile gets pulled downward, tracing an arc until it hits the ground. Make sense? Now, if you fire it faster, that arc gets wider and it travels further before hitting the Earth. So, the whole core concept of spaceflight is achieving an unimaginable horizontal speed. You want to widen that arc so much that as the projectile falls, the curve of its fall perfectly matches the curve of the Earth itself. It literally keeps falling, but the ground just keeps curving away from it. And that, my friends, is what an orbit actually is. Now, the difference between an airplane and a rocket? It is literally night and day. An airplane relies entirely on its environment. It pushes against air resistance to generate lift and stay aloft. But a rocket? It operates in the deadly emptiness of a vacuum. With absolutely no air to push against, it has to rely entirely on brute force propulsion and this continuous, relentless war against gravity.
Moving right along to section 2, reaching cosmic velocities.
Okay, so to actually beat that gravity, we got to cross a hard mathematical threshold, 7.9 kilometers per second. Just let that sink in for a second. 7.9 kilometers per second. That is roughly 28,000 kilometers per hour. At that speed, you could fly from New York to London in, about 10 minutes? That number is our absolutely critical first measuring stick for success in space exploration. We call this the first cosmic velocity. It's the exact speed where an object's forward momentum perfectly balances out the downward pull of gravity. So when a spacecraft hits 7.9 kilometers per second, it effectively stops falling back to the ground. It becomes an artificial satellite. It just coasts indefinitely in orbit around the Earth without needing to burn any more fuel just to stay up there. At this point, it has completely conquered the immediate fall. But hey, orbiting is really just being held captive by Earth on a slightly longer leash, right? If our ultimate goal is to leave Earth entirely, say head to the Moon or Mars, we need to hit a staggering 11.2 kilometers per second. This number is mathematically known as the second cosmic velocity, or as you've probably heard it called, escape velocity. At 11.2 kilometers per second, the spacecraft achieves so much energy that its path changes into a parabolic trajectory. It effectively snaps that invisible tether. Now, Earth's gravity will still pull on it, kind of slowing it down as it travels away, but that pull will never, ever be strong enough to drag it back. It has completely broken free from Earth's grip. And once we hit that magical 11.2 kilometers per second, it is a total game changer. We unlock the gateway to the entire solar system. Suddenly, the orbits of Mercury, Venus, all the way out to Pluto become accessible to us. We are no longer bound to our starting point. We literally become cosmic navigators, plotting courses across hundreds of millions of kilometers of empty space.
Which brings us to section 3, liquid and nuclear power.
Now, knowing the speed we need and actually achieving it, those are two very different things. To hit those numbers, we need serious thrust. On one side, we have traditional chemical liquid fuels, the reliable workhorses of the space age. But on the other side, we have the massive, almost sci-fi potential of nuclear propulsion, which really represents the next frontier of deep space travel. Let's break down the chemistry first. Inside a liquid-fueled rocket, it's basically a highly controlled explosion.
Powerful turbines pump a combustible fuel, like alcohol, along with super-chilled liquid oxygen directly into a combustion chamber. And remember, there's no air in space, so the rocket actually has to bring its own oxygen. They violently mix, ignite, and blast extremely hot exhaust out the back, which pushes the ship forward. But here is the catch. Even the absolute best chemical rockets max out at pushing a vehicle to around 4 kilometers per second. Wait, 4 kilometers per second? That's barely half of what we need just to reach orbit.
So that's exactly why scientists look to the alternatives. A nuclear rocket operates on a totally different principle. Instead of burning chemicals, it uses the raw, intense heat of an atomic reaction to instantly superheat a liquid, something like hydrogen or helium. This superheated liquid expands violently into a massively pressurized gas, blasting out of the exhaust nozzle at speeds that traditional chemical rockets could only dream of. The efficiency and top speed potential here are just enormous, and it effectively reduces the fuel mass you'd need for long-haul interplanetary trips.
And that leads us to our final part, Section 4, the multi-stage solution.
Okay, so we have a huge problem. If chemical rockets can only hit about 4 kilometers per second, how in the world do we ever reach 11.2? Well, the ultimate enemy here is dead weight. Imagine driving your car on the highway and literally throwing the heavy, empty gas tank out the window just to go faster. That's essentially the whole concept of a multi-stage rocket. Instead of building one giant rocket that carries all its heavy, empty tanks all the way to space, the vehicle is actually several independent rockets stacked together so they can actively shed weight mid-flight.
Let's see how this works in action. First, the massive bottom stage ignites, burning a truly insane amount of fuel just to fight through the thickest part of the atmosphere. But once it's empty, it doesn't drag that useless metal into space. No way. It dramatically detaches it, letting it fall right back to Earth. And at that exact second, the next stage up ignites. Because it's now pushing a much lighter payload in the thinner atmosphere or even the vacuum of space, its speed drastically multiplies. By stacking these stages, we compound the speed, finally allowing us to shatter that 11.2 kilometers per second barrier.
As we wrap up this explainer, we've seen how overcoming Earth's gravity requires not just immense power, but absolutely brilliant engineering. We have to mathematically plot our escape, harness incredibly volatile chemical or nuclear reactions, and literally throw pieces of our own ship away just to reach those required cosmic velocities. But I really want to leave you with this thought. Once human ingenuity fully harnesses these forces to permanently break Earth's gravitational chains, what magnificent mysteries in the dark void are we going to conquer next? Thanks so much for joining me on this deep dive, and I'll catch you on the next one.